afternoon, students. Welcome to the third video on ARM processors. Today we'll be seeing the video on flag register of ARM processor, which is especially the Cpsr flag register, which is nothing but current program status register. So let us see the details of this flag register, and also we will be seeing how these flags that are available in the flag register will help us in doing the programming. Now this is the overall 32 bits abbreviation of the Cpsr flag register. So here you can see that all registers in ARM processors are 32 bits. So these are the 32-bit description for the Cpsr flag register. So let us start from this corner, that is, we will start from the condition flags. So coming to condition flags, we have 4 condition flags in Cpsr register, which is N, Z, C and V. Now coming to the first condition flag is V. So this is the 28th bit of Cpsr. So whenever this V is equal to 1, that means a signed overflow has occurred. And whenever this bit B is equal to 0, that means a signed overflow has not occurred. In the next slide, I will tell you what is a signed overflow means. The 29th bit is the carry flag. So whenever there is an extra bit after the MSB bit, so that means it is taken as a carry. So whenever there is a carry after MSB, which is the most significant bit, then this bit is set equal to 1. And when there is no carry after MSB, then this bit is set equal to 0. So that is the 29th bit of the Cpsr register. Coming to the next one is your 0 flag. So here you can see that whenever the result of any operation is 0, then this flag is set equal to 1. And when the operation result is non-zero, then this flag is equal to 0. So these flags are set automatically after an arithmetic or logic operation occurs. And if we need, we can refer to these flags and make a branch decision or whatever we need. If we do not want, we can just ignore them, but it would be set automatically after arithmetic operations. The next very interesting flag here in ARM processor, ARM7 especially, is the negative flag. So far in the Intel processors such as 8086 and 8051 and all that, we have seen a flag called sign flag. So whenever the number is a negative number, the sign flag will be set equal to 1, and when the number is a positive number, the sign flag will be set equal to 0. But in ARM processors, it is no more called a sign flag, it is called a negative flag. So whenever the result is negative, this flag will be set equal to 1, and when the result is positive, this flag will be set equal to 0. So now let me just explain to you what is the relationship between, this is a very important point that we should be remembering. That is, what is the relationship between the overflow flag and the negative flag that is available in ARM processor. So it is very important. Once we are clear with this relationship between overflow and negative flag, when we discuss about the ARM instruction set, it would be easy for you to understand the instruction set, especially branch instructions. So now, before going into the relationship between overflow and negative flag, let me just take an example. Suppose you have a 8-bit register. First, let me tell you what is overflow. Suppose you have an 8-bit register, and that register can accommodate an 8-bit signed number. So in that case, the maximum 8-bit number, positive number that it, because signed, please remember, I am not telling a normal number, it is a 8-bit signed number. The register capacity is it can only accommodate 8 bits. So in that case, what would be the maximum positive number that it can accommodate? The 8-bit register would be plus 7F. So this is what is the maximum number. So here you can see that 7F, and this MSB bit is taken as a sign bit, so that is representing the plus. Now suppose you want to store a negative number in the same 8-bit register. The maximum negative number that it can accommodate would be -80. So here also the MSB is taken as the sign bit. So here 1 represents that it is a negative number. So my dear students, so this is the case for an 8-bit register. But we know that all ARM processors have a 32-bit. So only the bit size changes, but the concept is the same. Now let me tell you an example how these overflow negative flags work hand in hand. Now suppose you take addition of two numbers, plus 40 plus 43. Okay, so here you can see that plus 40 could be written like this and plus 43 would be represented like this. Now when you add this 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 0, 0 and so on, you get a number like, the answer should be actually plus 83. So this is the result. But what happens is, we know that the maximum positive number that an 8-bit register can accommodate is only 7F. But the result here is 83. So what happens is, the MSB bit here is actually 1. Whenever MSB bit is 1, it means it's a negative number. But in this case, it is not a negative number, but still the MSB bit is equal to 1. So whenever this happens, that means there is an overflow that has occurred. So that is how the processor understands. But ARM processors are having a better way of representing the negative flag. What they would do is, they would first refer whether there is an overflow. Whenever there is an overflow, the negative flag is not set just by looking at the MSB. What is MSB value here? It is 1. Whenever MSB is 1, what does it mean? It is a negative number. So just by default, it will not set n equal to 1. Why? Because it will go and check for the overflow. When your overflow is 1 and your MSB is also 1, your negative flag will be equal to opposite of your MSB. I repeat once again. In ARM processors, whenever overflow flag is set equal to 1, your negative flag will not be set just by looking at the MSB. Instead, it will look at the MSB. It will also look at the overflow. When both these, when overflow is set equal to 1 and then MSB is 1, your negative flag will be set opposite of the MSB. This is a very, very important feature in ARM, which is not there in Intel processors. Okay, let me tell you another example. In this example, we can see that we are adding two numbers, plus 23 and plus 31. The result is plus 54. Now in this case, it is within the 8-bit range, isn't it? Because 8-bit positive number can be 7F, but the result is only plus 54. So the overflow is not set. Now in this case, your negative flag will be equal to whatever is the value of MSB. So MSB is 0, so your negative flag also is 0. Why? Because your OR flag is not set. So to summarize this concept, because this is very important, this, if you understand this clearly, then ARM instruction set will be very easy for you to understand. So whenever overflow is set, your negative will be opposite of the MSB value, negative flag. And whenever overflow is not set, your MSB value will be set same as that of the negative flag. Is this clear to you? Okay. So this is about the relationship between overflow and negative flags that are available in the Cpsr register. Now coming to the next is, we have 2 bits for interrupt masking. So let us see what are the 2 bits. The first, the 7th bit is called the interrupt request mask. Now, since we have moved from studying Intel processors and then now we are into ARM processors, there are slight changes. Here also there is one major change. We have studied about in the previous units, we have studied about the um, special function registers that are available in 8051. Could you just tell me what is a special function register that is available to enable and disable interrupts? Yes, it is IE, interrupt enable register. But then in those registers, whenever you want to enable interrupt, the bit is set equal to 1. So when you set a bit equal to 1, that means you are enabling the interrupt. And when you set the bit equal to 0, that means you are disabling the interrupt. But here in ARM processors, it is just the opposite. Here the 7th bit is interrupt request mask, right? So whenever this bit is equal to 1, which means you are disabling the normal interrupts from occurring. Have you got the difference? So in case of Intel processors, when you set an interrupt bit equal to 1, interrupt enable bit equal to 1, it means you are enabling the interrupt. But here it is just the opposite. When you set the bit equal to 1, it means you are disabling the interrupt, or you are masking the interrupt from disturbing you or from occurrence. Similarly, when this I is set equal to 0, that means your normal interrupts are enabled, which means you are unmasking it and you are allowing interrupts to occur. Same thing is applicable for the 6th bit. The 7th bit is for normal interrupts, whereas the 6th bit is for fast interrupts. So in ARM, we have two types of interrupts that can occur. One is a normal interrupt and second is a fast interrupt. The difference between these two will be discussed when we discuss the operating modes in detail. Now same thing applies here. When this 6th bit is equal to 1, we are disabling the fast interrupt, or we are masking. And when this bit is equal to 0, we are enabling the fast interrupt. Okay, we are enabling the, or we are unmasking the fast interrupt. So please remember this difference between an Intel processor and an ARM processor. So the next one is a very, very interesting feature in ARM processor, the T bit. The T bit is the 5th bit. We all are aware that ARM processor is called as ARM7 TDMI, where the first letter T stands for thumb state. Now how this name thumb has arrived is, whenever there is an image, a smaller version of that image, we call it as thumbnail, right? So that is how the name thumb state. So your normal ARM state has got 32 bit instructions. A smaller version of it, which is the thumbnail version of it, is 16-bit instructions. So that is why the name thumb state. So thumb state means all instructions are 16-bit in size. We have seen in the first video itself in the RISC processors, we saw that all instructions are of same size. That is one of the main features of RISC processors. So if your ARM is operating in the normal state, all instructions would be 32-bit. But if your ARM is operating in the thumb state, then all instructions would be 16-bit in size. Yes, now whenever this T bit equal to 1, that means your processor is operating in thumb state, which is working with 16-bit operations. And whenever this T is equal to 0, your processor is in the normal ARM7 state, where all instructions are 32-bit. Now, there may be a question that is arising in your mind. Now, which would be more powerful, a 32-bit instruction or a 16-bit instruction? Naturally, a 32-bit instruction would be more powerful and it would be giving better performance than a 16-bit instruction. Then, why do we need a 16-bit instruction in a 32-bit processor? Isn't it? So that is a question that would arise in many of our minds. But let me just explain to you with a live example of some appliances. Now I have a mobile phone with me here, or you may be watching this, you may be watching this video either in a laptop or in a computer or in a latest smartphone. Now, what is the main feature that we look for in a smartphone is it should have very high performance, it should have all best features, okay, and it should be fast and whatnot, okay. So all these features should be very high. But then let me take another example. This is a AC remote. Now, when you compare these two applications, okay, do you expect a very high performance in a remote as you expect in a mobile phone? No. A remote just has to do its functionality. It has to switch on and off the AC. It has to, change the temperature, and then some few other operations that it has to do. But say suppose both are using ARM processors. Okay, this needs all full performance, so which means it has to be used under normal ARM7 state. But this application or this appliance did not use all the functionalities. It is enough that if it does just what it is supposed to do. But what are the concerns here is we are ready to pay a high cost for this, but this we need it at a limited cost, and it has to have other features like better battery life, longevity, okay, and it should be simple to use, and mainly the cost, okay, cost should be less compared to this. So this is the main difference between ARM7 state and the thumb state. So both, say suppose both are made of ARM processors, but this utilizes all the features. So it is the normal state, but this utilizes only limited features. Okay, but we are concerned about other performance criteria such as cost, battery life, and all that. So we make use of the processor in the thumb state. So this is the main advantage why we have a thumb state available in ARM processors. Let me also tell you one more interesting reason why we choose to use thumb state. So suppose you usually the memory size in your ARM processor ARM7 is, we all know that it is 4 GB, right? Because we have a 32-bit address bus, so 2 power 32 is 4 GB. I have taken a small example. Let me take an example memory which is just 1 KB. So 1 KB means you can have 1024 bytes. So now suppose I am I'm working with this memory in the ARM7 state. That means all instructions will be 32 bits. So 32 bits means it will occupy 4 byte, right? 4 bytes. 32 means 4 byte locations in the memory for storing one single instruction. So 1024 divided by 4. So totally how many instructions you can store? 256 instructions can be stored when you operate the ARM in a normal state. Now suppose you operate the same ARM in the thumb state. Okay, the same ARM is operated in the thumb state. Then what happens is you need not have 4 bytes for one instruction, because your thumb instructions are only 16 bits. So it occupies only 2 bytes. So 2 bytes means 1024 divided by 2. So you can store 512 instructions. Is that clear? So this is one of the major reason why for all applications we need not have 200 and you need not have the entire memory space to be used. So we only use a part of the memory. So this is known as code density increase. Okay, so code density increases whenever we operate the ARM processor in the thumb mode. This is one of the major advantage why for many embedded applications and appliances we prefer to use the ARM processor in thumb state. That is, we have all features of ARM, but at a lesser memory size, at a lesser at a better code density, and at a lesser cost. So this is one of the major advantage. Now coming to the bits 0 to 4. The bits, you can see that the bits 0 to 4 are used to select the modes of operation. So we all are aware that ARM7 has got 7 modes of operation. So these 5 bits are used to select under which mode your ARM processor should be working. So if the bits value are 10000, then that is known as a user mode. So this is the mode that is used for normal operations. Okay, so this is the 90% of the time your ARM will be operating in this mode, which is known as the user mode. The second mode is the FIQ mode. So the bits values are 10001. So this mode is otherwise called as fast interrupt request mode. So I told you that there are two types of interrupts. So whenever high priority interrupt occurs, and then automatically your processor will be set to this mode. Then whenever the bits are 10010, your mode is known as IRQ mode, which is called interrupt request mode. So whenever a low priority interrupt occurs, then your processor will move on to this mode. And when the processor bits are 10011, you call it as SVC mode, which is known as a supervisor mode. So we all know that we have a special feature called reset. So we can reset all the register values, and everything can be reset. So whenever you reset your processor, the default mode after reset would be the supervisor mode. And the next mode is the abort mode. Whenever your bits values are 10111, it is known as abort mode. So when you try to access your memory and your memory access fails due to various reasons, we'll be seeing that when we see the details of pipelining concept and all that. So when your memory fails due to various reasons, then your processor moves on to this mode, which is called the abort mode. The next mode is when your bits are 11011, you have an undefined mode. So here also, whenever there is an error that occurs in the instruction. So whenever an undefined instructions are encountered, so both these modes are whenever error occurs. Error occurs in memory access, it is abort mode. Whenever an error occurs in instruction execution, then it is undefined mode. Similarly, the last mode is all bits are equal to 1. This is known as a system mode. So system mode is a user or a programmer invokes the system mode where you can operate with the OS and memory capacity and all those details. So it works with the system. So these are the 7 modes of operation. So all the modes except user mode is called the privileged mode. Okay, but 90% of the time your ARM processor will be only operating in the user mode, and all other modes are whenever an error occurs, it goes to an abort or undefined mode. Whenever an interrupt occurs, it goes to an interrupt or fast interrupt mode. Whenever you want to change the OS or system functionality, you go into system mode. And so all other modes are special modes, but only user mode is a normal mode of operation. So to conclude in this video, we have seen about the Cpsr, and the reason why I have only given the explanation of Cpsr is Spsr is same exact replica of Cpsr. It has got the same 32 bits. Why? Because whenever an interrupt or an exception occurs, just these values of Cpsr are copied, and then it is saved into Spsr. That is why Spsr is called saved program status register. So we know that whenever an interrupt occurs, all these values are saved, and then we go into the interrupt service routine. So before going into interrupt service routine, we take the Cpsr value, save it into Spsr, and then we go and address the interrupt. And once the interrupt is done, we have a return instruction, right? So we have seen the details of this in 8051. So whenever there is a return instruction, we return back to the main program. So when we return back, we take the values of Spsr which we already stored, and then copy it back into Cpsr, and we start working with the normal program. So that is the reason I have not given the details of Spsr, because it is exactly the same as that of Cpsr. So my dear students, hope this video on Cpsr flag register of ARM processor would have been clear to all of you. I would like all of you to give a review on this video in your Google Classroom after watching the video. Thank you very much.